I'm not sure how long it will take me to go through the processes before I can give you a proper post-mortem. But whatever happens and however long it takes, this question is such a sweet question. It's such a nice question. I've never used it before, and I now realise that it's quintessential C, and it's so simple, but does require, and the word that I really love is understanding, particularly when you haven't seen the exact question before. I think 28 people, for some reason, decided that they wanted to use standard in, and that caused me an enormous headache. Of course, the test cases, of course, are based on using the command line. So when you write a program that expects standard in, the program just sits there and doesn't terminate. So when I was doing them by hand, every 1 in 10 basically programs just looped basically, or sat there, didn't handle the test case. Then I had to work out how to put a timer on them, so when they sat there for more than 5 seconds, I killed the program. That cost me some time to implement. So that simple thing, or simple misunderstanding of not reading the question and deciding to use standard in and to use A to I's and scanfs and all this stuff, which was completely unnecessary, cost me quite a few hours of work, so that I've now got a test suite which can handle just about anything you throw at me. It'll keep on going, because you have to remember the 335 sat for the examination. One student, I'm not sure if he's here or she's here, didn't do the first question. 334 submitted the result. I think that they're all got C programs in there. They all have at least 0 length. Can't be 100% sure, because my test suite just flies through the lot now, even when they hang and they loop, and there are all sorts of things that they do, and it goes through the lot. So I've got results. But now I've got to do, and I've got that for other questions as well, now I've got to go through and try to bring them into what I call a hierarchy. Those that are just complete rubbish, and those that do standard in, and then I have to look at what they do, and those that actually make a reasonable attempt but loop, take command line but get into a loop, they don't end, and then you just go up in sort of a hierarchy. And I think I'll probably end up, given that the mark will only be 2.5 marks for that question, each question is 2.5 marks for those 4 questions, then I can't go to too many decimal places, so I'll probably end up having 5 or 6 different classifications, and people were getting half a mark, 1 mark, 1.5, 2, 2.5, that kind of thing for the different classifications. That's best I can really do. I don't have to go down to the nth degree and say you're going to lose 1/10 of a mark because you've... Oh, one thing. 2 students submitted programs without a single space of indentation. Nothing, just whoop, down the side. You do that, you lose all my sympathy. I refuse to look at those programs. The moment I looked at it, I saw it, well, that's it, goodbye, I don't care what the program does. And we'll see what it does with the test cases, which I don't know off the top of my head what they did with the test cases. But even if there's 1 semicolon missing, the slightest problem with that program is just bad luck. I will not look at it. It's impossible to look at. You look at a C program, just 1 long column, and it's unreadable. Okay, so you're crazy, absolutely crazy for doing it. I can't even understand why you would even consider doing it. You've never seen a C program, certainly not from me, and I've never seen one on the internet that does it, and why you'd want to do that yourself, I had no idea. But okay, you take huge risks by doing it. And of course you've got to pass, even if you get through all the test cases, and I go back and have a look at the program very quickly, I'll be taking a fair whack off the marks. One student used continue statements, I noticed. And it's exactly what the problem isn't the continue statement as such. Very fine programs can be written right with continue statements. Very stylish programs. But in the hands of somebody who doesn't know what they're doing, it's a complete mess. And when I looked at that program very quickly, I thought, well, does this person know what he's doing? It's completely waste of time. The continuous statement had no impact whatsoever on the logic. So it's an example where don't use things when we recommend you don't use them unless you're extremely competent. Okay, they're dangerous in the hands of novice programmers. Like go-to statements in the hands of a very competent programmer, a go-to statement is not necessarily a bad thing. But in the hands of first-year students or first-timers, they're terrible. Okay, and the same applies to go-to statements and break statements for that matter too. Okay, that's just a general overview of where I'm at the moment. I'm going to try and get through this really quickly so that I can get you some marks and get you some feedback on how you're going. I'll put this question up. I won't put up the solution for a while because I really want you to test yourselves again. Sit down for 1/2 hour and do that question. If you don't do it in a half an hour, play with it and work out what's going on, what's wrong. I don't want to tell you any more about what's going on there. It's a very simple question. It only takes about 10 lines. Okay, you've got to reach the level at this stage of the course of doing that program almost blindfolded. So really, if you can do it in 10 minutes, that would be a lot better than a half an hour. Certainly, some of you, I think, may have got a bit of a shock with that examination, the style of examination, where I just want you to program. Do you understand what you're programming? Not difficult questions. A couple of those questions are very short, the solutions. But gee whiz, you can make it complicated. I've seen some of the programs for that, and they're very long, a whole page, complex, all sorts of things going on. And this is very simple. Okay, so I'll leave it there for you at the moment. That's just the first question I put up for week 6 exercises. I'll be putting up a lot more questions for week 6 very shortly. One question that I did have a number 5 question, which, talking to Mei Cheng, recommended I didn't include. Not so much because of the question itself, just because of the length of the paper. And that question was on linked lists. Now, I think linked lists are still just too hard for the majority in the course, given what I've seen already. Some of you with this, I've seen on the forum, there's a real active discussion on linked lists, so there's no problem with them, with you students at all. With others, they're just too complicated. If you're still getting your head around that, you've got no chance with linked lists. So I held off that wisely, thank goodness, but you absolutely will need them for the final examination. I'd love to have another quiz later in the year, so before the final, but no, it's just not possible. The logistics involved, the army of people involved, the organisation involved to get 335 people in all those labs is monumental. I hadn't realised. We were the only course, by the way, that had a midterm. The only course, which surprised the hell out of me. I didn't know that at all. It's my first time doing that kind of examination, and next time I'll have to reevaluate it, whether it's worth the effort. The really good thing from your point of view is what you should be really thankful for, whether you did well or whether you did even very poorly. Would have been a real learning experience for you. You wouldn't want to go to the final examination never having done a midterm and seeing questions like that, but maybe even more complicated. So you now know the style of questions. Some of you did some really strange things. One student, for example, I seem to remember, reversed 2 of the programs, got the names wrong. How you do that, I have no idea, or why you would do that. So they submitted question 3 for question 2 and 2 for 3. So my test cases went berserk. And what's going on here? And I had to look at it and say they've got the wrong names on them. Now that's something I would never have thought of to cater for. So they're the kinds of things I have to... So the nuts and bolts of what kind of exam, what do you do submit 1, submit 2, submit 3, submit 4, and editing a program and using DCC is very simple stuff, but you've got to know it, kind of thing. You've got to be aware of it. And you are all coming from different environments. Some of you would see this as a very, very foreign environment to be working in. So I hope you've learned a lot from that point of view. I'll try to keep the final examination as close to that as possible, unless somebody has something, some recommendation that they would like to make. I'm happy to make it better, but really we all need to be happy with the format, because I'm not testing format, I'm not testing your ability to edit. All I want to do is test your ability to understand reading the problem and implementing it in C. That's what it's all about, not the environment itself. Okay, so I'll add more questions, and the ones I'm thinking of at the moment, there'll be a couple of linked list questions, and then there'll be a couple of questions on heaps. I'll try to get them out really quickly so you have things to practice with, to practice on. Oh, just one thing, yes, just in case some of you would have been looking at that line there, I added that one just last night. That'll be a test case, it's your program. So if any of you think, well, my program worked fine, but looking at that, I don't know anymore, well, I have sympathy for you, because that is a pretty horrible string, and out of that string there are, in fact, there are 2 8s. There's an 8 here, and there's an 8 there, so that's where the 16 comes from, if you're understanding the problem. I hope everybody now at least understands the problem, even if you didn't in the examination itself, that what you want is simply count the digits anywhere on the line. The thing that made it such a nice problem, if you realise, thinking back, you didn't have to write a single statement which produced an error, except for the mallocs that you did. And I can't even off the top of my head remember which questions required a malloc. But that's sort of a given. I don't even count that. You didn't have to write any single error message. And in this question there's no error. Nothing can be an error. If there are no arguments, that's fine. Does nothing. If there's one argument that's got no digits, that's fine. If it's one argument, it's full of digits, add them up. It just finds digits and prints the total. Very simple. There are no errors. That makes it a lot cleaner to program. You don't have to think about all of the things that can go wrong. The finest programs to write are the ones where nothing can go wrong. Every possible program you can write, or every possible call of that program is fine, is okay. And there are very few problems which you can actually bring down to that, because there's almost always exceptions where you say, oh, something's not allowed to happen. Here, there's nothing like that. That's what makes it such a nice problem. I'll certainly be reusing that in future years. So I'll be looking after that one, that problem, keeping it for future reference. Okay, that's that. Now I want to, in the linked lists, I want to revisit that, because I don't think there's a lot of poor understanding of linked lists, what I've seen on the forum, and there's a lot of stylistic-y kind of things, how you call, what you call particular pointers, and when you traverse you sort of walk along a linked list, how does that work, what gets changed, what do you have to remember? There are some subtle issues involved here, and if you're not good with pointers, they look very complicated. When you understand what's going on, they're actually very simple. There are a few basic rules, and after that it just is so easy. It's almost childlike, a linked list. But it does take a certain amount of understanding to get to that point. So what I've done is I've actually rewritten that first little program, which just did a linked list of 2 nodes. I didn't really understand what I was trying to prove with that program when I wrote it years ago, And when I've rehashed it this session, I thought, what am I doing there? And I looked at it again, and I now understand better what I was trying to achieve. And I'll talk about that in a second. So I've got that program, which I now call 2 nodes, and then I developed the other program, which used to be called Woollamaloo or Woolly. I've thrown that away, that's junk. I realised, don't like it. It's too many things going on in there, too complicated in a way. Now, the program I've got that replaces it is more or less the same, but I think it's a lot cleaner. It doesn't get confused with characters and the string Woollamaloo and what's going on there, because that has nothing to do with the linked list concept at all. But it highlights something which I didn't bring out when I gave that lecture a couple of weeks ago. So let's quickly go back to this 2 nodes, what do I call it here, 2 nodes list. And the reason for this program is very simple. What is the smallest linked list program you can write? The smallest, meaningful program. Of course, you could have a program, a linked list of length 1 with a null terminator, but that's not meaningful. I mean, something that actually is meaningful is really a linked list. Well, you need 2 nodes, really, to have a linked list, which have 1 link and 2 pieces of data, a terminator and a start. That is sort of the smallest thing that you could build. Okay, that's the smallest list that you can build. So what's the simplest way you can build it? Well, this program here has the interesting feature, and I looked at it for quite a while before I realised what the feature was, and that is there are no loops in the program whatsoever. And that's important. It may sound silly and irrelevant, but it's important because it's part of the simplicity. It is just 2 nodes. I create them individually, L and M, and I put the data in them individually, into L and into M, and I free them individually, L and M. I treat them as sort of 2 brothers, if you like, or 2 sisters, 2 members of a family. They're linked. And the statement, I think, that epitomises this really nicely, which introduces the concept of linked list really nicely, is statement number 28, if I remember correctly. No? Yes, it is. Statement number 28. Element 2 is, what's the data in element 2? Well, that is n points to next, which points to data. And element 1 is just the data in L. Is it L or N? L. So we have the left one has its data, it's element 1, and you take the pointer from the left one to the next node, and its data is the second element. So we don't mention M, which is the second node, we mention M indirectly through L, through the link. And that's what a linked list really is all about, that you use the links to move through or to reference other nodes. Normally you use the links to step through the array, not the array, the list structure from node to node. That's the way you normally use these links. But you can use them to reference data in another link. Not backwards, only forwards, of course, in the normal one-directional linked list. So this simple little line, 28, which references data in the next node, is, I think, just epitomises what this little program does. Creates 2 nodes, it prints the data that's in the 2 nodes, just with reference to L, and then it frees it. Frees L, and frees M, and then detangles, untangles, removes the pointers. Okay, that's all I need to say there. That gives a motivation for that little example. It's only there to get you to understand what is the essence of a linked list without the programming. This is a complete system in itself. Now, when I say, oh yes, I do want to make the point again, because in the examination of all places, I was surprised by some people that had trouble with the idea of cleaning up, and I mentioned Heap to a few of you, and you looked at me very blankly. And I thought, oh, I don't think this heap idea has gotten across very well, so I'll just bring it to you again. The idea in that line 32, 33, 34, 32 and 33 in particular, then 34 and 35, where you're giving the memory back to the heap. Now that heap is a segment of memory. By the end of tonight, you will hate that word heap. Not for the reason you think. There's a lot more heaps coming, but it's not quite what you think. For the moment, the heap, what we're talking about, is a segment of memory that you can use as a programmer. That's what heap is, a segment of memory. You need the free so that you give back to the heap, to the computer, the memory that you have requested and been granted. If you lose a pointer to malloc area, that memory is lost to your program forever. That's called leaked memory. You have a memory leak. You've lost memory. You can't reference it anymore because you've lost the pointer to it. So you have to always guard the pointer that you get from a malloc with your life, in a sense. You have to protect that pointer. It's very important. When you're finished with that memory, you should free it, and that gives it back so that it can be reallocated depending on the compiler. I showed you that with GCC and DCC in that little program, That's different from tangling, dangling pointers, which is even if you've freed it, that's given the memory back, but they're still in that variable location, whatever its name is. I usually use the name first. You could call it start, you could call it beginning, you could call it just N if you like taking risks. Whatever you call it, that first address of that memory, even after it's free, still has an address in it. If you print the data at that address and you've already freed it, anything could happen. It's unpredictable. And these are very difficult problems to resolve because you'll get weird behaviour that you can't explain, and it won't even be clear where it's happening, where it's coming from, what line is causing it. You get very erratic, because it could work to a degree, but the data there is not what you think it is, because you did a free earlier on, which you've forgotten about, and you're reusing the pointer. Forgetting that, it's actually gone, so you've taken the data away, but you've still got the pointer there. So, to be safe, you put null into that pointer when you free. And that means that that pointer isn't dangling, pointing to some data that's non-existent. So they're the two concepts, leaking and dangling. These are great problems with pointers in C. You need to be really very well aware of them. So, I just put a little example there that you don't need to be afraid of using the links, and this is not recommended, and as I say, this particular line of code is unusual and clumsy, but you could add 3 nodes, data in 3 nodes, just by using the links. So A next and A next, and get to the data. Okay, so you're only using one link to get to 3 units of data just by using the linked list structure. There's nothing wrong with it, but it's risk-taking. And the one thing you absolutely have to do is none of those pointers, of course, next and next, can be null. Because if either of those are null, well, you're going to get a seg fault. The program will crash. So you must check the existence of those nodes. But that's by the way. So you can use those links quite naturally for all sorts of things. Now, what I do now in this, what was Woolloomooloo, which I've now called floating something, what have I called it? Linked floats, is the only difference between the previous program, the 2-node program, and this program is I'm using now 3 loops instead of treating them as individual nodes, L and M. There's no longer an L and M, there's a structure, a linked structure of an arbitrary number of nodes. In this case, I'm assigning, I want 10 nodes, and the first loop, there are 3 loops. The first loop is creating the beast, creating the linked list of max float nodes between line 32 and 48. That's basically the same as before. I've cleaned it up just a little bit. That one loop creates our linked list structure. The print, I've separated it out. I didn't want to, but I decided to for a reason, which I'll tell you in a moment, is our second loop, and that's defined above here, and there's our print. Is our second loop, so I use a print for a create, a print for a loop, a print for a print. I use a loop for a create, a loop for a print, and I use a loop to do the freeing. 3 loops. Now, no loops in the 2-code program, the 2-node program. There are 3 loops for the 3 actions in this program. Now, I use a for loop to do the creation, and the most important thing in here is, well, I've called the, it's storing a float in each node, and I've called the data ship, floating ship, just so that it's clear and it's separate and I don't get confused between that and the links and other things going on. All the housekeeping that's got to happen to keep to get the structure right and to print it and to free it all. The actual data that's being manipulated, just 10 floating point numbers, well, there's almost, you see that they almost don't occur. There's a couple of places where you actually refer to the data, and this is one place here on line 38 where the ship is assigned that number F, the floating point, which is the parameter in the for loop. So I make my node, I assign both fields in the data component in that struct. If it's a first time through, then I have to remember which node I've created. That N is the thing that comes back from my malloc. I remember it in first, and when I loop around again, I get a new N. Every time the N is set with from a new malloc. So that changes, but I've remembered the first one. So that particular if-else statement is extremely important. The first time through, I remember what my first is, and every other time, I backpatch. And if you think about it, it's exactly what you want. The first time through, I can't backpatch because it's the first time through. But the second time, third time, fourth time, fifth time, right up to the last time, I must backpatch, because when in line 28 was it, on that previous program, explicitly put the address of the second malloc into the link in the first malloc, here I need to do that. That's a process of backpatching, just a simple one-off backpatch. This is now automated in the sense that I, in the previous node, have to put in the link of the present node. I can't put the link in till I have the present node, the current node, the new node. And when I have that new node, I backpatch the previous node. So that else part is putting in all the links. And how can I use previous? Well, I make previous the current node when I'm finished. So when I go around the second time, previous is the first time, is the first node. And then I backpatch the second time, I'm backpatching the first. When I go through the third node, I'm backpatching in the second node. Very straightforward logic, very simple in a way. The thing is that you can use it every time with almost every single linked list. You need the same structure, the same pattern with every traversal of a linked list. The things you don't want to change are how you define the linked list, because you can get into trouble with the pointers. What's data and what's a pointer and what's everything going to. Now, when I uncreate or free the linked list, sometimes I actually say here somewhere, I'm destroying the linked list. It's interesting, you're constructing a linked list, you're printing out its contents, and then you destroy it. That's another way of looking at it. Uncreating it, getting rid of it, giving the memory back to the heap. And here that little loop is doing that. We walked through that last time, we worked through that last time a couple of weeks ago. Now, I start at the first node. As long as there are more nodes, I remember that current node before I get rid of it by freeing it, because I need the link to the next node. So I have to store the next node in a temporary location. Then I free my N, and then then my temp, which is where I stored it, becomes the next node. Okay, I need to store the link to the next node before I get rid of the node that I'm wanting to get rid of. Now, question to you, if after having done that, I then do a print first. Now, before we go to that, what happened? The previous print, which was on line 49, printed the first node in my linked list. What was in that node? Who remembers the program? What was in the linked list? First node, data. What are you talking about? Let's have a look at what's our first node? What am I putting in there? What's my data? 38. What is it? 0. 0.0. And the second one is 1.0, then 2.0, etc. There's nothing hard. Now, that's what first contained. Now I do print, I free it, and I try to print it. What does it do? What was that? Did you say something? No. Null? It prints null. That's a very good, very clever, not clever, it's sensible. Can't predict. See, I've got rid of the memory, so what kind of pointer is it now? It's dangling. I'm trying to print a dangling pointer. I've freed the data, and it somewhat depends on what, if anything, any malloc has come in and taken it in the meantime. Now, in your program, you know it's not, because there's only a few lines of code. Nothing can get at your area. So that won't be a problem. Well, as it turns out, it does depend on the compiler. DCC complains if you uncomment that line of code, and you should do it for yourself just to see. And what DCC says is when you do run it, it doesn't pick it up during compilation, but at runtime it says when you try to use a dangling pointer, you're accessing memory that's been freed. Error, and it crashes the program or stops the program. That's DCC. GCC, in contrast, keeps on going. It just prints out what's pointed to by that dangling pointer, and as it turned out, when I ran the program last, there were 2 zeros there, and it printed out a 0, then another 0, and that was it. And what was there, I don't know. It just happened to be what was in those locations, and that was what I got. So it's unpredictable. Next time I run it, maybe something else will be there. So GCC lets you get away with it. In other words, GCC doesn't protect you from yourself. It will happily print garbage, basically. It's what it's doing. It's printing what's pointed to by a dangling pointer. Now, okay, what happens then with previous? Remember, previous went to the previous one. Can anybody think that through? Remember what the logic of the previous? Previous takes n, and then n moves on to the next malloc. So the previous is always one step behind. N gets malloced, and the old n becomes previous. N gets malloced, and the old n becomes previous, so it's just one step behind. Any thoughts on previous? Anyone? Previous is there, it's... What does this do? If I uncomment that print, what it does is the same as with n. It's the same allocated area, it's been freed, and it's pointing to that allocated area. Okay, so the same thing happens. Okay, what happens then with print n? If I uncomment that. Someone? Not hard. Anybody thinking? No. It's fine. It's actually fine. By luck. Why is it fine? Why is it fine? Yes. The while loop, line 53, says until it's null, go around and free. And then, of course, when line 53 fails, then it is null. And when 53 is null, it jumps out and it gets to that line there, print n. What's n? Well, it's null from line 53. And so, okay, then you could ask, well, okay, n is now null. What does my previous do? What does print do with null? Now there's my print, line 13. Line 14 says, as long as it's not equal to null, you print it out, otherwise you just return. This is a nice little question I could ask, just to see if you're on the ball kind of thing. Naturally, you would think, with those three questions, with those three prints, that uncommenting all of them would, and you make some prediction, and the correct prediction is really, it's unpredictable what happens. And the compiler may or may not pick it up at runtime. At compile time, it doesn't. No. At runtime, it may or may not pick it up. That's the evidence of GCC and DCC. It's always interesting to try both compilers with issues like this, because it's a compiler problem or compiler issue, not a language. Nothing to do with the C language as such. But just by the logic as it is, this n turns to be n is okay. That's coincidence, of course. It's not by design. It's just when I did it, I thought, I'd better try n just to be sure whether it does the same thing. And my goodness, it worked. And I thought, oh, that's obviously why it worked. It's null in line 53. And that carries across to that print statement, which just prints null, which is not a problem for the program, so there's no problems in execution. Okay, they're the print statements then. The dangling pointers, first, previous and n, they've become dangling because of the freeing I've been doing up here. So let's not leave anything dangling and we'll make them all null. And then what happens if I do a print, well, I mean, I've given it a game away now. If I do a print first in line 64, again, for the third time in the program, this print first, this time, of course, I've now nulled the first. And I just showed you my print. If it's a null, it doesn't print anything. What's the print? It's happy. I could, of course, have a print statement, the print first. That print could actually pick that up as an error. But generally, I like not to report errors unless I know they really are errors, and it may be by design that you want a null to be just nothing, which is a perfectly good nothing to have. So that print will obviously work fine, and you can see all three dangling pointers have been nulled. And that is clean, elegant, robust, safe programming. Okay, I hope we're all on the same page here. We all understand now what it is to undangle or clean up the pointers that have been allocated by mallocs. And what it also means that if you lose a pointer, you will lose memory. Actually leak memory is I always find a bit of a strange name. Leaking, and what leak is a bit strange. What you actually literally do is lose memory. So you take memory out of your program's resources. There's memory you can't really use anymore as long as your program's running, because you've done a malloc and then you've lost your pointer. That's basically what it comes down to. So the memory's still there, but you've lost the pointer. The dangling pointer problem is almost the other way around. You've given the memory back, but you've still got your pointer. So they're the opposites of each other. You've got two things. You've got the pointer, you've got the memory. The dangle is when you take the memory away and you've still got your pointer. To what? To anything, to garbage. And the opposite problem is you haven't got a dangling pointer, you've got no pointer at all, and you've got the memory there somewhere, but you can't get to it. So the memory you've lost it or it's leaked. There's a really important concepts in C. Okay, so that's it. The rest of the slides are exactly the same. Now, to push this heap concept further, we're going to get on to heap data structures. Oh, I've got to log in. Didn't know that. Does it let me? Yes, it does. Now, heaps. And just to give you a bit of an overview of what we're going to try and do, we'll see how far we get. I'm not intending, wow, 3/4 of an hour to get to this point. Amazing. We're going to talk about heaps and heap implementations. And we're going to talk about operations and comparing heaps to normal arrays. And the last thing is converting an arbitrary array into a heap. So you can see a heap is a data structure. Now, what is he talking about? The segment of memory that I've talked in for 45 minutes on, well, say 30 minutes, that you use as by calling malloc, that segment of memory is called heap memory, to be accurate. Not just heap, it's heap memory. It's an adjective. It's not a noun. Heap memory. What I want to talk to you about now is a heap data structure. A heap data structure has nothing to do with heap memory. If you get those two things confused, you're going to make one hell of a mess of your final examination paper. Okay, and you'll confuse hell out of me when I'm trying to test your programs, and when I say heap, you're going to misunderstand what I say heap. Because, oh, he wants me to do a malloc, and your other program does malloc of 10 things, and you print out hello world or something, and I don't want anything to do with heap memory. I want a heap data structure. So be very careful that you understand the context of the two words, that term heap, in the context of a data structure and in the context of segment of memory. Okay, they're completely different. They have nothing to do with each other. A heap data structure is a high-level, two-dimensional data structure. It is high-level because it is higher than other things like linked lists and arrays. Linked lists and arrays are ways you implement things. An array as such is useless to you as an application, as a user. You don't want to see an array of people, really. What is an array of people? You want a list of people, and that may be implemented in an array of pointers or something, but the array is the implementation. It's low level, not as low as an integer. That's very low level. And bits and bytes, no, these are really low level. So we've got a higher level data structure. You implement, you create a heap by using either an array or a linked list in general. So they're higher level. Now what is a heap? Well, that's how you implement it. What is the heap itself, the data structure heap? It's a tree of data. It's actually a sort of an extension of a linked list. Whereas within the linked list we had data, link, data, link, data, link. But now we've got, of course it's a tree, we tend to go from the root down to the leaves, my daughters always scratch their head and wonder why I draw my trees upside down. Why are the leaves at the bottom, Dad? So, my root, 2 children, left and right. Not next left, next right, if you like. And the next left is another node which has its own next left and next right. So you can go down the left side by saying, well, what do I want to call it? The root, left next, points to left next, and you go down in a line taking all the links on the left side. So you have a 2-dimensional linked list structure, in effect. The irony is, and why life is not always as you wish it to be, is that the worst possible thing you can do to implement a heap data structure is to use a linked list. A linked list is a terrible implementation of a heap data structure. Terrible. They're probably worse. And what is the perfect vehicle for a heap data structure? It's an array. Array has some really beautiful, what would you call it, characteristics that make it really nice to implement a heap data structure. So a heap has a root node, and it has either 0, 1 or 2 children. So you may have no children, the root node may be all on its own, like A there. That's a heap. Well, it's a node, but it could be a heap. Or you could have just 1 child or 2 children. There you see 9 has got 2 children, 8 and 5. Okay, there's 2 children. That one would have been nice to have had one with 1 child. If it's only 1 child, it's got to be the left child. It can never be the right child. Just the right child. You must start with left. Here you see with the third one on the left, you see the D has a child, and it's a left child. E has no children, and F has 2 children. So they've all got 0, 1 or 2 children. You can have 2 kinds of heaps, and max heaps and min heaps. Just like you can have 2 orders, increasing order, decreasing order. A max heap is one where the root node of every subtree is the maximum of that subtree. The min heap is when the root node of every subtree is the minimum of that subtree. And this is the essential characteristic, or one of 2 essential characteristics of a heap. And you see that tree heap there, that's a max heap. And you see the left bottom subtree, 7, 6, 0. That is its own little heap, if you like, where 7 is the maximum of 6 and 0. To the right, 12 is a maximum of 11 and 9. Then you see 21 is a maximum of 7 and 12, 6, 0, 11 and 9. That bigger, if you like, heap. And then 15 is the maximum of 11 and 0, or bigger than maximum, is bigger than 11 and 0, and 78 is the biggest of the lot. Okay, so they increase as you go up, but we don't care which is greater on the left and the right, children. Either could be anything, as long as they're both less than or equal to the parent node. In a sense, this is sort of a family, cross-section of the family. You don't mind which child goes well or goes badly, as long as they stay under your control. As long as they stay under you, you're happy. Okay? As long when they rise above you, you've got a problem. What a heap is, basically. Now, the 2 properties, therefore, are the hop, the heap order property, which says for root node K for root node with key K, the nodes of each subtree have less than or equal to K, and the root of each subtree recursively down the tree satisfies the same property. The other extremely important property, which makes this all work, is what's called the complete tree property, the CTP, but it's a bit wrong actually. It's really better called the almost complete tree property. I'll actually say that there too, and that is that you must always fill the nodes from top to bottom, left to right. There may be no holes in the tree. So you see that left tree, for example, the right node is not filled in, but that's all right. If a new node comes along, it must go here. And then if another node comes along, it must be the left node of this left branch. And then if another node comes along, it'll be the right node of this node with only one child. You must fill in the children from left to right, top to bottom. That is a rule. So that is not a complete or almost complete tree. It's incomplete and does not satisfy the condition of CTP, often referred to as a CTP. It is, in other words, not a heap, the one on the right. The one on the left could well be a heap depending on the values, of course. It must have the right values. In other words, the values satisfy the hop. So if you like, the hop are the values, the CTP is the structure. Both have to be correct always. Provably correct, if you like, for your heap program to be correctly working. The idea of a heap, and you saw that with the structures above here, is order. Not too much and not too little. If you have an ordered list, getting an ordered list together, that's a lot of work. That's possibly n squared, depending on the length of the list, hence n squared amount of work. N squared is a big number and then gets big. Sometimes you want a little bit of order, not everything ordered. You could want, for example, to know what the maximum is in a list. But you don't care about the rest, as long as you just want the maximum. Now, if you think about it, and I'm sure most of you have never thought about it, and I've had research problems where you only want the next maximum, and after that you don't care what the rest of the list is, whether it's ordered or not. And what you'd normally do is, I want the maximum, I'll have to order the list, and there's n squared, bang goes my program, it's going to take forever. Performance is gone. What have you done? You overkill, just like the way you did the midterm examination, particularly question 1. You overprogram it to the death, to your death. You haven't thought the problem through, and if you just need the maximum value in a particular dirty big long array, is there a way of structuring that array that you can really quickly get that maximum value, and that's it. So at every moment in time, you always have your maximum value available to you. And you think, well, isn't that ordered? No, it's not. It's not ordered. Because the rest of the list, the rest of the array is all over the place. Except you always have, in a heap, the maximum at the start. The rest is junk, if you like, unordered. But you absolutely, with guaranteed, 100% certain, the maximum will be at the start. That's what a heap gives you. And there are a surprising number of problems where that's enough. And the performance gain that you get from doing that into having a data structure where you have one guarantee in life that the maximum is where you think it is, and you can get at that at constant time, the performance cost is log n. And you should remember that log n is almost flat. Linear is that, quadratic is that, exponential is more as that in comparison. Okay, so we've got a real slowly increasing, almost completely flat log n function. Log n is a very slowly increasing function. So with that small cost, you are guaranteed in a heap to have the maximum element, the minimum, available to you on that one spot in the array. That's the whole point of a heap. If you get that in your head, a partial ordering, just the maximum, it's always there, and the amount of work I've got to do every time to keep that so is only log n. That's almost nothing. So heaps really pay back. One of the applications of heaps are in priority queues. Priority queue, what's that? Well, the priority queue is where the queue, if you like, the array, the data, the thing at the front is the highest priority. The thing at the front is the thing we need to address first. The thing at the front is the maximum or the minimum, and the rest is in some sense irrelevant. And if you take the thing at the front away, the rest of the queue will and put the next maximum in there very quickly for you. Because of the partial order structure, it can do that really quickly. And you'll see very shortly, when I show you some programs, how it works. And it's almost a bit magical. You sort of have to get your head around it a little bit. It looks a bit programmy, but it really does work really neatly. It's very robust. Sort of can't go wrong as long as you have clean programming style. Okay, so I've gone through the two properties. Again, the order property is the values, and the CTP is the structure. Because of the complete tree property, and this is where structure is so important, I said that CTP means that you always fill in the nodes when you add a node to your tree in the bottom, in the top down, left to right order. So you start at the top and you look for a place to put it. So you look for the last node that's gone in, and it's either the first child or second child of an existing node, or you become the first child of a new node, or you become the second child of a previous node. So the number of nodes in such a tree is going to be, at level 0, which is the root, there is one node. At level 1, there are two nodes, the left and right children. At level 2, 0, 1, 2, they're going to be 2 squared, 4. The next level will be 8, next level 16, etc. So the number of nodes will be the sum of 2 to the 0 plus 2 to the 1 plus 2 to the 2, etc. The number of nodes for an n-deep tree will be 2 to the n. So 2 to the n will be represented in a tree that is going to be log n high. The depth of the tree, maximum depth of the tree, is log n. The tree is pyramidal, triangular. Well, of course, it could be a bit jagged at the bottom. It doesn't have to be completely flat because you don't know. The numbers of nodes won't necessarily be exactly a multiple of 2 to the n or whatever at any level. So you have one partially filled. There may only be one node at the bottom level. So it's going to be 2 to the n minus 1 plus 1 kind of thing. And the rest of the leaf nodes, you can say, are sort of, there's space for them, but they're not filled in yet. And they will be filled in if you get more nodes. What's extremely important, and which gives us the performance, is that the height to get from the root to any leaf is never more than log n. That's the property of having that structure, the advantage of having that structure. The characteristic of that structure is you have a log n depth. The maximum height of a heap is log n, and the maximum path depth is hence also is order log n. Heap implementations. An array is the most efficient way. Ironically, a heap data structure, this two-dimensional sort of linked list, in a sense linked list, can't or can be, but is not efficiently implemented using a linked list. Now, of course, with a linked list, the thing that tells us, or the thing that we do with linked lists is we're mallocing for every node. And where we're mallocing, we're getting heap memory. So the irony is not only that a heap doesn't get implemented well with a linked list, in spite of the fact they're both from the same family of data structures, but the heap segment that you're using, the heap memory that you're using, is not something you need in a heap data structure. They don't go well together, in a sense, the irony. And the array, which is just a fixed length piece of data structure, that goes perfectly. That is very useful to implement a heap. And you very quickly understand why in this next slide here, this next part of the slide. It's because of the CTP property. Because you know the structure, you can predict the structure. When you have a parent, you know exactly where the children are, if any, in the tree. You know the length of the tree, the number of nodes, and you also know for every parent where its children will be, and for every child where its parent is. That fact, and that fact alone, means that you can access, not only just randomly, you can access individuals with absolute certainty. You know where the children, what the structure is. So you don't need a special pointer to tell you the next link is, or the left child is, and the right child is. You can work it out on the fly with a very simple formula. And just look at what's happening here. At location 1, sorry for the poor thing on the right, I must change that. Poor diagram. The T is in 1. We forget 0. The Americans like to use 0, I notice, for their heaps. They often talk about 0 being the starting point. And I'm happy to get rid of 0 because it makes the maths just a little bit simpler. So, we put node at index 1, the root node at index 1. Its children are going to be at 2 and 3. Their children are going to be at 4, 5, 6 and 7. To go from 1 to its children, you multiply by its position by 2 and multiply its position by 2 and add 1 for the right child. So 2 for the left and multiply by 2 plus 1 for the right. That also applies for the children. So to get the grandchildren, or the children of 2, which is Q, you multiply by 2 and you get to the left child of Q. And you multiply by 2 and add 1, you get the right child of Q. To get the left child of K, it's multiply by 2. There's no right child. But you will know that when you run the program, because the number of nodes are finished. It exceeds the number of nodes. So you won't try to access that location. So in the array you have T, Q, K, M, A, H stored in 6 locations. Always refer from 1 onwards, talk about 1 onwards now. And the 6 locations refer to that heap. That is the essence, that is the kernel of all of this. The nucleus, the heart of a heap is that there. An array is a totally perfect way of storing a 2-dimensional structure which has a wonderful partial order property where the maximum is at 1. That is what a heap is. Or minimum, of course, but let's just keep it simple. So in this particular case, I've gone through and said, well, T has 2 children, and they're at 2 and 3. Q has 2 children, K has 1 child, etc. More than that, who is the parent of Q? Q is at 2, so if you're at 2, I'm at index 2, who's my parent? Whatever my number is, I divide by 2. Okay, and 2 divided by 2 is 1. And 3 divided by 2 in integer arithmetic is also 1. So both 2 and 3 have parent 1. For the first time in your life, you'll probably see a real advantage to integer arithmetic. Just by rounding down, when you do the division, forget the remainder, you get at exactly what you want. So to compute the parent from the children is trivial. You take whatever index they are in the array, and if it's, let's just say it's 2Q, or not 2Q, I won't use 2, if it's location 100, where is 100? No. Where is the node or the heap node at index 100? Where is its parent? It'll be at 50. Okay? Where is the parent of 50? It'll be at 25. Where is the parent of 25? 12. Where is the parent of 12? 6. Where is the parent of 6? 3. Where's the parent of 3? No. 1. That's the root. Okay, so I've just gone through about 6 generations. Parent, grandparent, great-grandparent, great-grandparent. I've just gone up the tree. Just divide by 2. And every time it takes me with absolute certainty to the parent. There's my structure. My God. You never want to touch a linked list again. This is heaven. You are all love arrays. I know that. And this is exactly what you always felt and dreamed, that life can just be an array. And that's what heaps are. It's just one big array. And there's order there, and there's structure there, and it's fast. It's log n. So in a sense, it's dream time. It's paradise. Now, what can you do? Well, the best thing you can possibly do is get the maximum. That is really snack easy. Just grab the first element. You've got him. What's the maximum by heap? Take the first element. By definition, by structure, by everything you can name. The top element, the first element, is the maximum, or the minimum if you want to take the min heap. So that's a constant time. Costs you basically no time to do. Doesn't matter how big the heap is. The heap could be from here to Alaska. It'll cost you 1 nanosecond to get the maximum. Now, inserting an element, wow. You could think now, okay, what do I do with an insert? Now, let's look at that structure there. What am I going to do? If I now want to insert a letter B, B. Well, there's only one thing I can do because of CTP. You know, one of the questions I asked a few years ago with the examination, what does HIP stand for? What does CTP stand for? I'd be surprised how many students didn't get those acronyms right. What does CTP tell us? Well, it tells us that the tree's been filled in properly, and therefore a new node can only go on one spot. You can't leave holes. You can't put it in weird places. There's only one place that B can go, and that is as the right child of K. Now, if I made, let's make it really interesting. Let's make the new child Z. Okay, we've got a problem. We've got CTP. We ain't got any hop. We've lost the max property. So what you need to do is you need to heapify. We heapify the heap. Another name for heapifying is we do a fix-up. We fix it up. Up being the operative word here. We go up the tree fixing the problem. So when we insert a node, we put it in the array right at the very end. That's always right by CTP. You think, wow, is that true? No matter how long the array is. Doesn't matter how complicated in a sense or how big this heap tree is. And there's all sorts of partial order structures in there. You've seen them. Sort of the maximum and then the subtrees have got to have a maximum and all this business. When you get a new element, you just put it at the end. Hey, CTP happy. Wow, that seems like magic. But yes, it sort of makes sense because every time you get a new node, it's got to go top down, left to right, and therefore the next available spot will be the next spot in the array at the end of the array because there can't be any holes. There can be no holes. It's just the definition of CTP. Okay, so I put it in on the end, but I've broken the hop. It's no longer got the order property. Well, what we do know is where the parent of the newest node resides, where it is in the array. And if we put him in at position 100, last entry was 99, and now I'm going in at 100, where is 100's parent? It's at 50. Oh, I know where my parent is. And if I'm bigger than my parent, I swap with my parent. Oh, okay, so if 50 is smaller than 100, I do a swap. Now, I've now got 50 bigger than 100, but if 50 is now bigger than 25, its parent, well, I've got to do that swap again. And if 25 is bigger than 12, I've got to do that swap again because I've got to get the maximum up to the top. I heapify, I fix it up by doing these swaps if necessary. If I get to a point where I'm smaller than my parent, say 12 is bigger than 25 after I've done the swap between 50 and 25, well if it's smaller then my parent, after the swap, end of chain. I don't do any more. I'm finished. I've heapified my tree. It's back. I've got hop again. I've got the heap order property. Now it's almost ridiculously simple, because what we're talking about now is we put a node to the end of an array, and then we start jumping or referring back to half the offset that you're at, or your index that you've currently got. And you do comparison, and if you're bigger, then you go back. As long as you're bigger than half of the index that you've got at the moment, you keep going back until you're no longer bigger, and then you stop. That's heapifying it. That restores the order. By definition, you've got CTP. When you've got hop, you're finished. You've inserted a new node, and you've got your heap back with the new node in it. You've successfully inserted a node. So I've explained it to you in words. The programming is, well, the one thing I didn't say in all of that, and some of you may have been thinking, I'm not sure, but the word I didn't use is recursion. It was just an iterative step that I kept halving until the last step would be, if in this case here, if I added Z at location 7, I compare that location 7 with half of 7, which is 3. Z is greater than K, therefore Z and K swap. Now, Z at 3 is still greater than T at 1, so I swap Z and T. Therefore, Z is now at the top, T is at 3, and K is at 7. That's the new heap. I stopped when the division by 2 gave me the root. I always stop when I finish when I get onto the root. So it's an iteration. And how many steps are there? Well, log n steps. Depending on the number, you just take the log of that number off the number of nodes, take the log of it, and more steps you can't do. It's never big, well, relatively speaking. So that's what fix-up does. It heapifies in the up direction. And here's the program. And I explained in a lot of words, and you're all becoming more C-ish in your style, and maybe you think, well, I didn't understand all that English, but let me look at the C program and then I'll understand completely. I'd love to think that was true. So here's the program, fix up. It takes an array, star heap, integer star heap, and it takes a child. Now that child is an index. If the child is greater than 1, so I've got some child that's not the root, and the parent's child, the parent is less than the child, okay? I've now got the indexing going here. I've got the child, that's the index of my new node, and I've got the parent, which is child divided by 2. If they're the wrong order in a max heap, then I do a swap. So the lines 4, 5, 6 are a straight swap, and I do child is child divided by 2. I go to the parent and do it again with the grandparent, and then I go to the grandparent and do it with the great-grandparent, and I go to the great-grandparent and do it with the great-great-grandparent until I get to the root, till I get to the original. Now that simple little piece of program there ensures your heap stays correct. It stays a heap. There is in some sense no correct heap, because as you could well imagine, with this partial order property, all that you know is that a parent is greater than the children, but they could be in either way. And there are many, 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 many trees, finite number, which will order them differently, and they'll all be good heaps. They'll all have CTP, they'll be beautiful triangles, and they'll all have the heap property, HOP. Okay, so that simple little program, yeah. So how many actual lines? 1, 2, 3, 4, 5 lines really. What took me 10 minutes to explain. And here we take, I don't like the example very much, I really want to change it one day, but and do some pretty diagrams. But so starting with an empty heap. Now, of course, when I can insert a node to the end of a heap, go to the end, I can actually start inserting from day one, moment one. I can have an empty heap and insert something. And that should insert it at the root. And then I can have a heap with just one node, the root, and then I can give it a left child. And with a heap which is a root node and a left child, I can insert a new node, which will become its right child. And then if I insert another node, it'll become the left child of the left child of the root, etc. Okay, so I can build the whole tree now from nothing just by doing this insert operation, where every time I read a new number, I have to do a heapify, because when I insert a child, that child may be bigger than the parent. So every new insert requires a heapify to make sure I don't destroy the hop, the property of heap order. So add T, so I've got my first node, M will become the root. Add T, is it complete? Well, tree is a root node with the left child. Is heap order violated? Well, T is bigger than M, therefore there has to be a swap between T and M. And if you look here, the M is the first node. We add T, heapify, that makes T the root. Then we add H as a right child. It's in the correct position. No, the heapify does nothing. The first double, remember that was a while loop with two conditions. The condition that the child is greater than the parent is not true, therefore it doesn't do anything, jumps out. Then we add what's the next one? The Q is added to that position where the M is. Now Q is bigger than M, therefore a heapify will reverse the two. So every time we add a node in the correct position, that's CTP, we will do an automatic, we will execute the heapify function, those 5 lines, to make sure that the ordering stays correct. And that's the final tree when we add all the nodes. That does mean, and that is interesting, that if you change the order of entry, of entering MT, H, Q, A, K, you change that order, you will get a different heap. Okay, the order is important because it means who's left, who's right, and the whole structure sort of changes. Well, the structure doesn't change because it still remains a heap. The CTP is ensured, but the labelling will be slightly different. But it'll always have the one thing that doesn't change, is the root will remain the biggest node in this particular case. Okay, now, two really important things, operations in any data structure, arrays, linked lists. First was insertion. Well, how do we delete? Now, the one, you could say problem, but this is really depends on the application, is you don't use a heap if you don't want the max or the min. If you're interested in the second biggest or third biggest, well, even then, that's not true. But if you're interested in some arbitrary node in the middle of your heap, don't use a heap. The heap is there for the max. And it knows where the max is, and after that it doesn't know. Could be the next second highest one could be, I'd have to think about that. Where would it necessarily be? What are the possibilities? Well, could get a bit greyish. Where is it? You have to work on that. But you do know where the max or the min will be, the first position, and that is the application where you'll use a heap. You wouldn't use it for anything else. So if you want complete order and you want the third, the fourth, the fifth, the sixth, the seventh, the eighth biggest node, you need a full sorting algorithm, and that will probably be n squared. But if you're happy just with the best or the biggest in your application, heap is perfect because it gives that to you in constant time with a log n algorithm. That little heap function I showed you, that heapify, is log n. It goes through log n times, n being the number of nodes, and the loop dividing by 2 means it actually circulates around, circles that loop, log n times. So, the delete operator now, if we want the maximum, the minimum, we want to take that out. Of course, just like a stack or a queue, we take out the element we want, we look at it, we want it, we take it out, and of course that means things have got to be rearranged, because all of a sudden we've got a hole at the root, and there's nothing worse you can imagine for a heap than having a hole at the root. That you just can't have it. It's got to be something there. And it's got to be the max, otherwise the next time you want it, it'll be gone. You just can't have that. You've got to fix it up. So what we do is we take the root node out, and then we think about it. What do we do now before we go and have a look at the code? We try to understand, well, I've got a root node, and I've taken it out. What do I do? Any suggestions? Put something back. That's very good. That's amazingly sensible, and you're on the right track. What could you put back? Somebody else. What are the options? You create another hole.
The right was bottom line?
Yes. You're smart. You're very clever. That's very true. The only one that we know we can take away, which has no children guaranteed, is the last node. The poor sod that came in last, well, poor sod, he's actually turned out to be lucky. He's going to go straight to the root. He's been promoted. Over everybody. He just goes whoop up to the top. Okay, so we've lost the last node. We absolutely have not destroyed CTP, have we? Clearly not. We just got rid of the last node, which was the bottom, top down, left, right, the bottom. We just got rid of whatever that was, the last node. It's a dangling thing, if you like. We got rid of him. We put him at the root. We got our CTP back. Well, we've got the hot problem now because God knows what we put up there. That thing may be worth nothing. So what do we need to do now? Fix down. I love him. And heapify, both. Okay. That's right, we heapify. We heapify down or we fix down. And how do we do that? We compare the root with its children. Now, got to be a little bit more careful because there are two children. When we were a child, we've all been a child, which some of us maybe still are, we have a parent. We have one parent. Well, it's not true, is it? Well, we have sort of one parent. One parent pair, if you like. That's an identity. Goodness. So we have one parent, so it's clearly who the parent is. But when you are a parent, you have two children. So if you are now checking the value between you and your children, which is what we need to do with heapify, we need to say, okay, I have to be, as parent, bigger than my child. So if if I get promoted from the very bottom, right down the bottom of my heap, get promoted right up the top, and my value is 1, and then my child is 100, well, obviously I shouldn't be up at the top. I heapify by reversing the two, swapping. But what happens then? My two children, one is 100 and the other one's 60. And I have value as parent of 1. 100, 160. I'm smaller than both of them. Which way do I go? Okay, which way do I go? What do I do? What's my dilemma is I've got two choices. They're both greater than me. Which one do I pick? The greater. You do pick the greater. You must pick the greater of the two children. So if you have two children to choose from, one is 101 and the other one is 100, and you are 99, you've got to swap with 101. And then the issue then becomes, when you become the child of yourself, in a sense, the parent, you demote yourself to be the child. You then say, okay, my grandchildren. Who is the greatest of my grandchildren? I must swap with them. if I'm smaller. So you heapify down the tree. Each time you swap, and the irony, you could end up exactly where you came from, but the process has, well, not quite the same thing because you've lost one node, so you can't be exactly the same position. No new node has come in, so you could be next to where you were before. That depends completely on the values in the heap. So deletion is exactly the same as insertion, but you go down instead of up. Okay, you take something out, you plug it up with the bottom node, and you heapify down. And heapify down could go boom, 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 all the way going down, but left and right, left and right, left and right, till it gets to a leaf. And it stops, of course, at any time when you find that you are indeed bigger than both your children. Okay, it's very simple concept, very simple conceptually. It's an algorithm, it's a step incremental process, and the rest is just programming. I don't have to go through that anymore. And here's the code that does it. It's even shorter. Just look what that code does. There's one thing about heap code, there's not much involved. As long as it took me to explain that, it is so easy to code. You look at it and think, wow, is that right? Is that all? I have my heap. I have a length. I need to know the length of the heap. The value I want to return, remember I'm deleting a node. So the first thing I do is I get the root out. That's my return value. That's what I'm doing it for. I want my maximum node. The application wants it, I farm it off, call it retval, return retval. End of story. That's my step. Important step's got to be done. I've delivered. But now I've got a heap. Fix my heap. And the way I fix my heap is I put the node at the end, I put it up to the front. See, well, that's easy. You don't want to think about doing that with a linked list. If you've got a linked list and you've got to do that, oh my goodness gracious. And it's an exercise I'm thinking about getting you to do. Not in the exam. Okay, that would break your hearts. And you'll be throwing rocks through my windows and everything. It's a horrible problem. So if you're going to move the top to the bottom, the end to the front, it's messy. You've got to go all the way back, remember where we were, and go all the way, and then come all the way. Horrible. So that in an array is, with a heap, it's just so easy. And then in line 4, we call fix down, which actually does the incremental step process, just like fix up. Fix down, also called heap down. If a node is smaller than others, to swap with the last child means simply to move a node to its correct place downwards, has complexity order, log n. Why don't I have the code here? Why don't I have the code for fix down? Can't think of it. I would fix up. It's almost identical to fix down, but you go the other direction. Maybe I've still got it coming. Okay, so here's the example. Well, we're going to get rid of t. We get rid of t, we put h where t was, and then we do a fix down, and the fix down says we have to replace the biggest of the two children at 2 and 3, which is q and k. The biggest is q, therefore we do a swap between q and, k and h. So q goes up to the top. Now h is still bigger than m, so we do another swap, and it's bigger than a, but m is the biggest, so we do a hm swap, so we're at the leaf and then we're finished. So what we started with was a 6-node heap, and now we've got a 5-node heap that's been reheaped. It's still CTP, and we'll return the maximum value. Well, that was a constant operation. We just returned the t almost immediately. Oh, there's fix down. Why did I do it so late? Okay, the fix down is where we're actually going. We've first got to check the, as long as you have children, you make sure that you are still got children that you can look at. You take the child, which is always at times 2, the left child. If the child is less than then, and then you've got to compare the two children. the left child and the right child. That's really tricky, and it doesn't make me proud to have programmed it that way. But you see, the heap child is less than heap child plus 1 in 6 is doing something just a little bit sneaky, and that says if the left child is bigger than the right child, then I increment my child by 1, which in other words, I want my right child. So it's either going to be child or child plus 1, depending on the relationship between heap child and heap child plus 1. Understand? Left and right. That's all it's doing, comparing the two children, to finding which is the greater of the two. And when it gets out of that in line 8, it then says, okay, I now want to compare me as parent and the child, whichever one it has been, whichever it was, child being the left or the right. I then do a swap if the relationship is wrong to reheat my structure. And I keep doing that until there are no more children. And that is the 2 times pair. Because I can double the index until I reach the end of L, my length, len. When it gets greater than my length, no more children. I've reached a leaf. The last one was a leaf. This one is slightly less, what would you call it? The reason, the problem is, that complication is what's happening in line 5, 6 and 7 to decide which is the greater of the 2 children. That's a separate little thing. I need to know which of my 2 children is the greatest. And then in line 9, I do the comparison with that child. It's simple, but you've got to be a little bit careful that you get the numbers, the index is right. Mathematics is on your side. Doubling it is all that you need to do to get to a child. And you can sort of see how important that is. The halving it when you're going up the tree and the doubling it when you're going down the tree. Okay, I show you here what happens if you don't. If you were to swap with the smallest child, you could get yourself in a situation where the heap is no longer correctly ordered, but I won't go through that now. Well, I think we might go through this little thing. It's a bit boring, but I might cut it at some point. Oh, no sound. I had that problem last time. I cannot for the life of me. How do you do sound again? It's here. Anybody know? No, that's that sound? No, that's going. Oh my goodness, I forgot that. Stop. Go back. Why can't there just be one control? Turn on subtitles. Mini player. I just got to be sound. I did it last time, but what did I do? Messages? Tube apps? I did it. What was it? Look at. When it comes on, it's going to come on with a blast.
Have to change from the control panel of the mic.
Everything here is on.
25, a right child can be bigger than 17, a left child. In this case, you can even get sort of a node weight. It's a perfect, sort of complete binary tree. Well, if you have so many nodes, the count of nodes where the last level isn't exactly complete, that's fine. The last level will be filled in exactly from the left. So the shape of the tree is always, the shape of the heap is always going to be something like this. Another important property is, in this case, I'm dealing with a max heap. You look, the value stored at each node is larger than the value of either of its children. So 45 is larger than both 33 and 3. 33 is larger than both 17 and 25. And on the other hand, there's no, we don't know anything about left child versus right child. So 33, the left child can be bigger than 3, the right child. 25, a right child can be bigger than 17, a left child. In this case, you can even get sort of a node way down here on a low level, having a higher value than a node quite high in the tree, but it's not a direct ancestor. Okay? So those are the two properties that we're going to have for a binary max heap. Each node has value larger than the value, larger or equal to than the value of each of its children, and the shape of the tree is this perfectly balanced binary tree. Okay? So, because the tree has such an explicit shape, unlike a binary search tree or something, you don't have to explicitly represent nodes. You don't have to sort of say, oh, here's a node, and here's its left child, and here's its right child, and maybe a node we can have a pointer to its parent. You don't need that because the tree is so regular. We can just say, you know what, I'm going to store the root of the tree in the first position of an array. Its left and right children, I'll store in the next two positions of the array. And then sort of take nodes in that order. Just read off from left to right at each level. So I got 45, 33, 3, 17, 25, negative 34, negative 55, 4, 14. I just stick those into an array and I know, hey, 3. What's 3's children? Well, node 3 has as children 1, 2, 3. Has as its children the 4th, 5th, 6th, and 7th positions. Okay? And node 3's parent is in the first position. Okay? So we can sort of formalize that and say, if we're indexing from 1, then the index of a...
You can see why the difference, all the Americans, I've seen all the Americans always use 0 as a starting point for the root node. And not sure if it's British or European or Australian even, that we start with 1. Makes the maths easier because the left, to get the left and right, hang on, am I right? Oh, take it back. I'm jumping ahead. He's starting from index 1.
Twice its index. If the index of its right child is 1 more than that, and the index of its parent is the index div 2. Of course, you can index from 0, just sort of knocks everything over by 1, that's fine. But here, we have this nice implicit array representation of a heap where you don't have to have references or pointers to other nodes. Okay? So great. Next thing to think about is, how do we insert? How do we insert into a heap? So I have this heap, and I know what the shape of the heap will be like after I insert something. I can imagine I insert. The shape is going to be like this. I have an extra node, and it's got to be filled in from the left. So the shape's going to be like that. And I fill in something. I fill in whatever it is that I'm inserting. So in this case, if I'm inserting 22, there you go. I insert it, and it's there. And this 22 is the left child of the 25 nodes. Okay. So right. The other thing that we have to worry about, of course, is each node has to have, as a parent can have a value no larger than its parent, right? A parent has a value at least as large as its children. In the case of this 22, we're fine, right? 22 isn't bigger than 25, so we're fine, we're fine. Move on. Okay, now we're going to insert a different value. We're going to insert a 39. Well, in this case, we see We know its position. We know where it's sort of what the heap should look like. We just try to insert it there, and everything looks good, except 39's parent has a value smaller than 39. So what I'm going to do is I'm just going to swap 39 with its parent. And now, great, 39 and its children look good. But of course, 39 still could be bigger than its parent. Oh, I'm going to swap it with its parent. I'm going to just keep on moving it up.
I think we'll stop it at there because you can watch it in your own time. It's just going to repeat everything I've said before. You've seen the program, so in a sense, a third repetition of this. Get rid of that. Oh, I should actually, okay, go back, doesn't matter. That was the fixed down animation. Now, why are we doing this? What's the point? The bottom line, the thing, the magic, is log n. That's the answer. Any question about heaps, priority queues for that matter, the chances are very high that the answer to that question, whatever the question is, log n is going to be the answer. Because that's the big thing it's got. If you've got an unordered list, then you can insert an element into an unordered list, of course, anywhere basically, at the end, but at the start in a sense, if you've got room, if you like, you can put it there. It'll always be a constant operation. But to find the maximum in an unordered list requires you to look at every single one of them. That's n, that's linear. If you have an ordered list, we can find the maximum, we can find the maximum or the minimum really quickly, but to insert a new element, we need to do a linear search to find the place to put it. So either way, we're either going to have a linear handicap cost to put them in the list or to find them when you use ordered and unordered sequential lists. When you have heap order, to insert its log n, to get the maximum time is constant plus log n to heapify. So both operations are log n. So that's the magic of heap. With ordered and unordered lists, you have a basically really fast access in one, either insert or delete, and terribly slow in the other, linear, if we could call that slow. When you have a million or a billion or a trillion elements, then linear is slow. Log n is peanuts, it's nothing compared to linear. There's no cost greater than log n in heap insertion and deletion. It's all governed by the height of the tree. So heaps are very fast in comparison. The interesting thing, and I did ask this question once, remember, was you can get yourself into the heap way of thinking and think, okay, I understand what a heap is now and I can heapify up and down to get it right depending on whether I'm deleting or I'm inserting. Okay, I understand all that. But then a heap is actually just an array. It's just an array, and if you didn't know it was a heap, you wouldn't know that it was a heap. There's nothing to indicate that it's a heap. Okay, you look at the array and maybe it's the biggest numbers on the left there, but there's nothing to give away that it is a heap. You don't see that easily. So I take here the case where I've got the heap, the array called heap roses. Just obviously a flower, a name. Represented as a heap, if I actually drew that R-O-S-E-S, well, I forget about the zero element, okay, we're not worrying about that. So roses in my array. So if I give you an array with your name or my name or UNSW in the name, whatever string I give it, you can draw the heap. Of course, you know where the root is, where the children of the root are, where the grandchildren, where the great-grandchildren are. You know where they all are in the heap. So if that array is a heap, you can draw it. So every single array that you can think of, you can draw and pretend it's a heap. And then, of course, the question is, Is it a heap? Does it have the heap property? The array that you've been given, has it been heaped or heapified or not? So here we have roses, and that's clearly not a heap. When you look at it, so R-O, R-S, S is at the bottom. S shouldn't be at the bottom, S should be at the top. So that's not a heap. Okay, so that's, I mean, talking about another level of course, but a simple question. I'll just give you a string and say, is that a heap? And the string could be something like, it's nice weather today. Okay, and you say, well, is that a heap? Now, you just think, how would you know if that's a heap or not? If you didn't know what a heap was, you wouldn't have a clue. I mean, it just would mean nothing to you, that question. But for you, you just say, well, I know how to draw that. It's nice weather today, I-T-S-W-E-A. You write all those letters and you put it into this beautiful triangular, with maybe a bit of a jagged bottom structure, and then you just check all of the bars, and you see whether they're all alphabetical. Be interesting to actually think of are there good English sentences or words? Are there heap? Oh, isn't that interesting? I've never thought about that. If I ask you a question, give me a word that satisfies heap. That's heap. Give me a heap word. Do you understand the question? I've never thought about that question. Give me a heaped word. A word that satisfies the heaped property. So just kangaroo. You draw it as a tree. Well, there's K is pretty good. Oh, O's, of course. Okay. Okay, but you've got to get that ordering in there, but it's not alphabetical. It's not you're not trying to find A, B, C, D, E, F or Z and go backwards. That's not what you need. You need partial ordering. So there are a lot of words which are not alphabetically decreasing, but nevertheless there's some partial ordering there which would make them a heap. And how many words are there in the English language which are heaps? That's a very interesting question. I've never thought about that before. Really interesting question. And that would be, I mean, you'd be battling in an exam and say, what's a heap word? And then you're going to, I can imagine the scribble paper, all the words you'll be trying to think of. And words that start with Z, presumably, would be very favourite. Zanzibar. Ooh, how do I write Zanzibar? N-A-N. No, that's not going to be right. You need the second letter, can't be an A. That's horrible. So you want Z, X, I don't know, how many, maybe Z's not a good starting point. There aren't too many words start with Z. Let's go back down. Maybe if we start with a W, we've got a more chance. And then you think about what's a word, a four-letter word, which has the heap property. It's a great question, actually. It really makes you think. So in any case, here we have roses. That's not a heap, and we need to do a couple of things to make it a heap. So when something is not a heap, there are actually, you can use fix up and fix down. When you have a string, an array is a string, basically, just the letters one after the other, immediately it's a heap-like, in the sense you could treat it as a heap. But if you do, you've got to make it a heap, and that means you've got to heapify. And we've seen heapify up when we insert it, and we've seen heapify down when we delete it. And in fact, you can do either to fix your string. And it'll only take a few minutes, it's more or less at the end now. So here we have method one, we use fix up. We build the heap by inserting one at a time. So you take the R, the first letter, you take the next O, you put it where it should be, the first child, and then you take the S, the second child, and then you see straight away, every time you add a letter, you do a heapify on the latest letter. So when you put the O in, that's okay. When you put the S in, you've got a problem. S is greater than R, so you have to do a heapify. So that means you rearrange it to, so you've got SOR. And now you add the E, left child of the root, and then you add the S, another problem. S is bigger than its parent O, therefore you swap the S and the O. And there's your heap. So that is the heap representation of roses, which is interesting. And again, we come back to the question, using the algorithm here, how many words are their own, how many words require no actions by heapify? Fix down. Or fix up. Or the alternative is to use fix down. We consider each character in reverse order. So basically you go from right to left and insert into a heap using fixed down. So we fix down from n to 1, so you go from right to left, you go for nth position S. S is wrong. S shouldn't be where S. I've got roses as my starting point. It's not heaped. And we go backwards up the tree. So heap